Again, how to solve for the coupled linear differential equations, and we need new tools. And the tools basically, in simple words, is we're going to convert the coupled differential equations into a problem we call the eigenvalue problems. So that means the tool I'm going to introduce to you is the eigenvalue problems method, and the techniques for solving eigenvalue problems we're going to help us to solve for the multiple degree freedom systems here. So again, from this point onward, that will be the key of the key for you to be successful in. Again, we have one final exam, and pick that one. This is a key, really is a key for doing good. Okay, I will try my best. And so this is the contents I asked you to quickly go over here. So this we are given a matrix. Okay, so for the matrix, each one the horizontal we call the row, vertical we call the column. Okay, and the n we denote the size of the matrix is n by n. The first one is indicate the number of the row. The second one indicate the number of the column. Okay, and if the number of the row equal to the number of the column, then we call that matrix called the square matrix. Okay, so just like this is a 2 by 2, 2 by 2, 2 by 2. They are squared matrix. And for our equation of motion, we always deal with is a square matrix. A few terminologies, for example, transpose. Transpose is like this. For example, if we have, say, 1, 2, 3, 4, 5, 6, if we consider this is the 3 by 2 matrix, okay, and transpose, we use the notation, and we just put the superscript and T. That means we're going to transpose this one, and the operation of the transpose is this. Look at this carefully. We simply tilt the column into row. That's it. So the first row, the first column becomes the first row, so that is 1, 3, 5. Then the second column becomes the second row, 2, 4, 6. Okay? And the trace determinant inverse, the trace is not important. Determinant and inverse I'm going to introduce in the next page here. Continue. I think the determinant something will be later introduced. So this is the basic properties. The summation of the two matrices of the same size, their transpose will be individually applied. So that can be distributed law. And alpha is any constant. So, for example, if say I multiply with my right hand. So, for example, if here I multiply with 2, okay? And the result of this simply is this. This constant simply individually multiply with each element of the matrix. This one we call the element, okay? And that is a has 6 elements. So this basically that is become 2, 3, something like this. Okay? So that is the second property like we did here. Multiplication of the two matrices, their transpose simply is if you want to distribute, then simply reverse the orders. Transpose of the transpose basically become itself. Okay, those are the basic property you can directly apply them. And I is called the identity matrix. Identity matrix, for example, sometimes you can see the people say this 2 by 2, so that means is on the element 1 in the, we call it, this called the diagonal, okay, and off diagonal equal to 0. So for example, the M matrix is always diagonal. most of the time, I would say most of the time, for all vibrations, the mass matrix are almost always diagonal. Okay, this is not. And so for I 3 by 3, and that is the 1, 1, 1, and 0, 0, 0, 0, 0, 0, like this one. Okay, in MATLAB, if you want to use I, and I think you're going to use EYE 3. I think that is a command in MATLAB to produce such an element here. Okay, so this saying, the multiplications of a matrix by identity basically equal to itself. Just simply 2 by 1 equal to 2, 3 by 1 equal to 3, kind of like the scalar the application multiplication. Okay, and this is a 0 element, so basically it's a 0. We have something like this one. Okay. Okay, now we come to here define the symmetric. Symmetric is that the matrix equal to the transpose of itself. That's called the symmetric. So you look at this one. This matrix is called symmetric because you can see once we take transpose how do we do it? We convert the column into row, convert the column into row. Basically, it becomes itself. So that's called symmetric. Okay. And in the similar definition, we have the skew symmetric. That means the transpose equal to inverse minus of itself. And this one we barely seen in our vibrations application, so you don't need to pay attention. And orthogonal, that by definition is transpose multiply A equal to identity. This one I'm going to use a lot in control, but not in this class, so we can skip off. Also, we have to concern with the determinant, and later on, I think I will give you the definition of determinant. No, here in my slides, I don't have that one, but I will exercise with the exercise to do the determinant. Okay. So that is the quick review about the algebra, linear algebra, and then I'm going to get into this very specific topic in linear algebra, and that is called the eigenvalue problems. And usually these kind of the problems are more than at least easily occupy one chapters of the linear algebra, sometimes extending into 2 chapters. So this is a heavy topic, and this is important. I will try to get this done in 10 or 15 minutes. So I will try is only get the portions we needed for our calculations. Okay, for the remaining, if everyone is really interested, then you can go forward. I think there's quite a bit books available in our library. Okay, so here let us first talk about what is the eigenvalue problems. You look at you can read the slides and carefully read the content. I don't think here this is a very good English. They call it plain English. I will try this one simply copy and paste from somewhere. But anyhow, the eigenvalue problem is this. We given a matrix A, okay. Usually here we talk about in specific A is a square matrix, for example, n by A. And the eigenvalue problems can be extended to non-square matrix, but that is a different story. So we know the contents, okay. The eigenvalue problems involve the determinations of 2 things based upon A. There exists a spatial some spatial number, scalar number. Here, the scalar is the terms we use in linear algebra. Because in linear algebra, sometimes we talk about is a matrix, say 1, 2, 3, 4, or sometimes we talk about vectors. Vectors simply is a column-wise matrix. Okay, so we talk about the matrix or vectors. And how about this? This is called the 1-by-1 matrix. Sometimes we give the name. This is the 1-by-1 matrix. And we simply, sometimes we call it scalar. So you know the scalar, that means a single term, the single number, we call it scalar. Okay. So the scalar numbers, lambda, and some column vector, x, and sometimes we use notations and or use with the notations x. Okay. So here is my notation, also textbook notation. They use square brackets for matrix. They use the kind of the angle brackets for vectors. Okay. So this is the angle. So such that this given matrix multiply with such a spatial vectors. So simply it's something like this. For example, say this is the 3-by-3 vectors, and multiply with 3-by-3 matrix multiplied with the 3-by-1 vectors. Okay. This result will become exactly equal to lambda times x. So basically, given any square matrix A, the eigenvalue problem is to calculate what is this lambda and what is this spatial vector x, such that this condition exists. So that means this A times x usually after operation will go to the different numbers, but on the spatial arrangement, that can simply is a scaling in the same direction of the x. So that's called the eigenvalue problem. If you haven't been exposed to this topic, you have to get used to just about the description of the problem setup. Okay. So again, we are given A. Then basically we're going to find lambda and x. Two terms, we're going to find it. If we given A, then how do we calculate this one? And this is a very special situation, and actually these appear a lot in engineering. We only given us one piece of information. We need to find the two pieces, and this one is very unusual in terms of our concept. And in this, we define the lambda. It's called the eigenvalue, and corresponding vector we call the eigenvectors. Okay, so that is the definitions of the eigenvalue and eigenvectors. So we are given A to solve for this equation. That means we're solving an eigenvalue problem. So this is what we defined as the eigenvalue problem. X equal to lambda x. Will be okay? Okay, so keep this in mind. Then here is a few examples here. How to solve for this one? Let me utilize the the 2x2 matrix, for example, here. Okay, so for example, say A equal to A11, A12, and right now I'm using the index notation. This is called the element, 11 element, 12 element, and this is A21, A22. And again, the notation of these indices is such that the first one indicated is the number of the row numbers. The second one is called the column number. If you remember, this is the first row. This is the second row. So this is the first row, so that is the 1. And the second column, this is the first column, second column. Okay, so that's a notation for 1, 1, 1, 2, 2, 1, 2, 2, etc. Okay. So if we are given this one, then basically eigenvalue problems can be described by this. A11, A12, 21, 22, multiply with the vectors is x1, x2. Okay, and equal to lambda, x1, x2. Okay, because this is the constant, and with our property, they can distribute into each element, so that is lambda x1, lambda x2. Okay? And here I'm talking about is the solution process. Okay, so this one is called about the solution process. Let me utilize the 2x2 simple example to demonstrate the solution process. And before we reach that conclusions, and here we can do a little bit. So right now, let me expand it to the two terms here. And this is the two equations equal to this one. So that means A11, x1 plus A12, x2 equal to lambda x1, right? And again, expanding the second equation, that is multiplied with this equal to this one, A21, x1 plus A22, x2 equal to lambda x2. Are we right? Okay, and then I keep continue. For the first time, I do this very in detail, but later on, once you get used to right away, you can jump the detailed steps. So this one, basically right now, let me move the right-hand side into the left-hand side and combine the second term together. So that is A11 minus lambda times x1 plus A12, x2 equal to 0. The second equation is A21, x1 plus A22 minus lambda, x2 equal to 0. Okay? So with this one, again, let me write it up into the matrix form again. Okay, so basically this one becomes is this A11 minus lambda, A22 minus lambda. Okay, so that is the final form we want to achieve, and the process can be actually written in very concise way using the matrix form. So basically, those steps can be replaced by a very concise process like this. The lambda This matrix, these vectors can be described by 1, 1, 0, 0, x1, x2. Again, here I use the properties at I times x equal to x itself. Okay. Any identity multiplied with any quantity equal to the quantity itself. I use that property, like 1 by 1 equal to 1, 1 by 2 equal to 2, the similar way. So in this way, that becomes lambda, lambda, 0, 0, x1, x2. Okay? So basically here, we want to say is this equal to lambda times I, the identity matrix. Okay, so this is what I need. Based upon this, equal to this, then that means using our notations, ax equal to lambda x, and basically equal to lambda times I times x. Okay, so that means a minus lambda times I times x equal to 0. So basically here, follow up this detail, that is explanations. If we do this step by step, expanding, but if we like to use the very concise the notations in borrow from linear algebra, we can write this. So that means from here to right away to here, I write it up here, we come like this. And again, that is explanations like this one here. Okay? So keep this in mind. Then basically here, what we're going to do is we have this one here. And so this page is not that important. So let me basically explain by that things here. This one, let me skip out this one. Keep this one. So let me summarize. So that is the problem statement, and I can tell you usually there's more than one eigenvalue and the corresponding eigenvectors. For example, if A is the n by 1, n by n square matrix, then you should expect the number, we should have the n numbers of eigenvalues, we should have the n numbers of the eigenvectors. Okay? So the solution process is like this. We simply say define the lambda and x. Okay. So this one we're going to solve is ax equal to lambda x. Okay. And right now from here we summarize simply that problem become like this: a minus lambda I. How about this? And let me use the notation, simply use the bracket to indicate that is a matrix. That'll be easier for us to see. So I write it up in such a concise form. And again, if you feel not familiar with that one, again, refer to this detailed process. Everything being written here that basically once expanded, that will be just like this one. Yes.
So you say find n eigenvalues. But
yes.
I thought the eigenvalue.
I would say lambda 1, lambda 2, and lambda n. And right now I simply use this as the generic notations.
I thought the proof said that the eigenvalue was a scalar. Did it not
Yes. The eigenvalue is a scalar, but there's a there's a
we're
different.
finding n scalar values.
Yeah. Yes. Okay. So corresponding, let me call it 1, x2. So there's an n set of things. Okay. So right now we come to this one, and then the next step is this. Any question? Yes.
For a given matrix A, is there like an infinite number of eigenvalues and vectors?
For if that matrix, the n is determined by the size of the matrix.
Oh, I got it.
Yeah. Okay. So that one basically to this step basically summarize what we have done in the last 10 minutes. And to proceed, and here, then right away to jump into this step here. Step 1, we're going to solve for these equations. The step 1 is this. We determine lambda. And lambda, there's the different numbers of lambda by this. This one, if you expand it, let me again using this as an example. This once expanded, once you expand this term, it will be something like this one. Okay? If you write it up, if you are given A, you simply write it up element-wise, and that will be like this one. I want everyone to be clear about what we are doing. Will be good?
So, question. Sorry,
yes.
So if I just don't understand how the idea of if we're finding n eigenvalues meshes with
yes,
the eigenvalue inside the formula there.
Yeah, and give me a few minutes and we'll get there.
Are there multiple eigenvalues per
We'll
matrix
get there.
that work? Okay.
Yeah, we'll get there and keep your question in mind. Okay, this one basically representing is the two equations, or equivalent to that would be n set of equations. Those equations something like this one here. If you look at the two equations or n set of similar equations, they are linear dependent. If you have remembered, if you have taken any linear algebra, not linear algebra, any fundamental algebra, have you learned the term linear dependent equations, right? What I mean? You pick up the terms, and you should know what that means. Let me make one example here. X plus y equal to 1. X plus 2x plus 2y equal to 2. In theory, we have two sets of equations and two independent variables. In theory, we should be able to uniquely solve for x and y, unless they are dependent, just like this one. So for this one, you can see definitely no. Very apparent no, right? So that is what we call the linear dependent set of the linear dependency, right? And this one, exactly the two equations exposed will be just like this one. Okay, so that means for any similar equation like this, we wouldn't be able to solve for the unique value for x and y. But what we know, we would know the relation between x and y. That is the most information we can extract. Are we right? Very straightforward, right? Is that right or not?
I think when you do an example, it'll make more sense.
Yes. So keep this in mind. Okay, keep this in mind. So basically, this equation, in terms of the symbols, although we don't know the lambda, we're going to deal with such equations. For linear dependent equation, actually dependency like this one, and equivalent to say is this. We're asking they are in linear portions. Okay, so that means the coefficients of the set of equations are in linear linear proportionality. So that means this respect to this one must be equal to this respect to that one. Are we good? Okay, keep this in mind, and then to implement that statement in linear algebra, we simply is to do this determinant of A minus lambda I equal to 0. And let me remove the bothersome. I don't like the unnecessary symbols, so why not from this moment, and I simply just like this. In some textbook, if you keep in mind, some textbook using boldface for indicating that is a matrix, but in writing, let me get rid of the unnecessary symbols. Okay, and what this means determinant. Determinant, yes. From ES301, hopefully you still remember how to calculate the determinant of a matrix. And let me make one example here. 1, 2, and 3, 5. Okay, so to calculate determinant, basically that one is equal to, look at this carefully here. That is the multiplication of the two numbers, that is 1 by 5, minus multiplication of the two numbers, 2 by 3. So the result will be equal to minus 1. For 3 by 3, in a similar fashions, the summations, this one, multiplication of the three numbers together, plus the three numbers, plus the three numbers, and minus multiplication of the three numbers, plus these numbers, and this number, and let me write it out. So that will be 1 times 5 times 9 plus 2 times 6 times 7 plus 4 times 8 times 3. Okay? Minus 3 times 5 times 7 plus 6 times 8. Something like this. And for the manual calculations, most of the time, with this one, we can handle the 3 by 3 at most, at the best. If you're going to handle the higher dimensions, then we have go to the minors or determinant formulas, and that one available in 301. And here, I don't want to go for that one because we don't have time. And if we go to the higher dimensions, then we simply go to MATLAB, the computer program, to solve for that one. Okay, so that is the one. So to determine this one, then we come to the A minus the lambda I equal to 0. Okay, so from here, let me use this example here, A equal to 1, 2, 3, 4. So for example, if A equal to 1, 2, and using that example here, 2, 4, okay? So that means we're going to calculate A minus lambda I, and that means going to calculate determinant 1 minus lambda, 2, 2, 4 minus lambda. Again, right now I directly applied these contents here. Again, you have to keep in mind this is a very concise writing. This writing is simpler is with this one. Okay, now I'm going to implement this one equal to 0. So we see how to implement the determinant. We simply duplicate this process. So that means 1 minus lambda, 4 minus lambda, minus 2 by 2 equal to 0. Is that right? multiplication of the two elements minus multiplication of the two elements equal to 0. Good? Okay, now let me implement. So that means equal to lambda squared minus 5 lambda plus 4 minus 4 equal to 0. So therefore, lambda equal to 0 and 5. So this is our eigenvalues. So therefore, are 0 and 5. So we solve our first question's eigenvalues, 0 and 5. Okay? Step 2, and going to answer your questions. The step 2 is this. For each of the eigenvectors, we have okay, so that is our problem statement here. The eigenproblem statement here. So for each eigenvalues, so say lambda equal to 0, we plug into here. 1 minus lambda, 2, 4 minus lambda. For this case, we plug in lambda equal to 0 and x1, x2 equal to 0, 0. And we solve for x1 and x2. We see what happens. So when lambda equal to 0, this value becomes 1, 2, and 2, 4, right? When we introduce lambda equal to 0 to here, that matrix becomes like this one. And multiply with x1, x2 equal to 0, 0. And you see this is the linear dependence. So basically this is equivalent is x1 plus 2x2 equal to 0 and 2x1 plus 4x2 equal to 0. This one apparently is linear dependent. We're not able to solve for the unique value, but we can solve for the relation. Right? We can solve for the relation. So that means from here we know the x1, x2 will be in such a relations. For example, we use either equations, this one, that means is this one, or using the second equations is like this one. So by using either equations, we know the relation is x1 equal to minus 2x2, right? That is a relation. So therefore, x1, x2 equal to, for example, say, let me use in alpha, this is if x1, if x2 is alpha, this is minus 2 here. Alpha can be any constant. 1 and minus 2 of the alpha give us the relations. Okay, so what is our answers for eigenvectors? This is our eigenvectors. Eigenvectors simply describe the relations. This is the eigenvectors associated with is these eigenvalues. So for each particular eigenvalues, we have associated particular eigenvectors. And I think that answers your questions. This is the first eigenvalue. We have the first eigenvectors. Again, we can repeat with the same patterns, and probably you can do it. Right now, if we replace lambda equal to our second value equal to 5. If we replace lambda equal to 5 introduced here, can you repeat the process? Can you repeat the process to find the second eigenvectors? Do it, and then compare with the slides. Okay? I know today, in about 20-25 minutes, I impose